So the Test of Time Award, as you know, is given to foundational work that really shaped the way we think about problems and really continues to inspire to this day. And this year it was given to two papers that pioneered the study of games played by learning agents. So the papers are Calibrated Learning and Correlated Equilibrium by Dean Foster and Rakesh Vora, and then a simple adaptive procedure leading to correlated equilibrium by Sergiu Hart and Andrea Mascolel. So Sergiu Hart will be the speaker. So Sergiu is a professor of economics at the Hebrew University of Jerusalem. Is also the founding director of the Center for the Study of Rationality. Has received many awards like the Rothschild Prize and the Israel Prize. Was the president of Israel Mathematical Society and Game Theory Society, and many other things. But I would just leave to Sergiu to talk about the award paper.
Okay, so thank you. On behalf of all four of us, I will try to tell you something about the test of time. And okay, now why can't I? Okay, so here are the two papers that were mentioned in the award. The paper by Dean Foster and Ricky Vora. You can see that that dates a few years ago, almost like 30 years. It took a few years for it to get published. And I know from personal, what the authors told me, that their paper was just desk rejected again and again because nobody would believe the result. It took them 7 years until it was published. The second paper is the paper of Andrea Mascolel and myself. By the way, this presentation you can find on my webpage together with papers and links and so on. So you are welcome to look at it because, again, I don't have much time to do things. There is also a collection of papers that Andrea and I published, things that came out of that paper and related material. On calibration, there is a nice chapter in the Handbook of Game Theory, Volume 4. And you'll be surprised, but Dean Foster and I are still working on calibration even nowadays. In fact, we even have some new results as of a few weeks ago, but I won't tell you about that now, okay? So I was wondering what really is the test of time. Probably you are wondering too. So I think it's quite clear something like 25 years of work probably qualifies, but you are wrong. That's not really the test of time. The test of time is to present 25 years of work in 25 minutes. That is the true test of time. And let's see if I can pass that. That's going to be much harder. Okay, so again, my talk is going to be an overview very fast, and let's see how much I can succeed in getting through. Now, let's see, I started at, what time did I start exactly? It was not 6, it was 6:05, 6:03, something. Okay, you let me know when the time is up, probably. So let me start with calibrated forecast. So what is calibrated forecast? So once upon a time, before most of you were born, forecast used to be, tomorrow there is going to rain, or tomorrow there is going to be sunshine. And then, you know, tomorrow it rains, everybody says, oh, this weather forecaster has no clue what he's talking about. So weather forecaster got much better and much smarter. Nowadays, in fact, many years now, they don't say tomorrow it's going to rain. They say the chance of rain tomorrow is 70%. And it doesn't rain tomorrow. They say, look, I didn't promise rain. I just said 70%. Problem solved. Nobody laughs anymore at forecasters, okay? But the question is, what does it really mean when a forecaster says the chance of rain is 70%, okay? How to interpret that? So the first notion, or a simple notion that was introduced, is the notion of calibration. And what does calibration mean? We're not going to say that the forecaster is calibrated. If we look at all the days when he said 70%, and we count how many of those days there was rain, and if that proportion is close to 70%, then we are happy, or he is happy. If that is true for every forecast that he used, for every 70% or 60% or 20% he used, so when he said 20%, the days that he said 20%, the number of rainy days should be about 20% of the number of days that is set 20%. If that is true for every P, we say that the forecaster is calibrated. Very simple definition, but it's not easy to, you have to start thinking a little about it. Okay, so now let me tell you something. I never studied meteorology, weather forecasting, earth sciences, cloud formation, anything. I mean, I studied some other things and I have some other expertise. So here's what I can do. I can guarantee, I can get you forecasts, and I can guarantee that they will be calibrated. And by guaranteed, I mean, no matter what the weather will be, you can put me any place in the world that you want, and I'll generate a sequence of forecasts that will be calibrated, no matter what the weather will be. So not only in Israel in the summer, where for sure there is going to be no rain, and that's very easy. No matter in the world. In fact, I can even take, let's say, the chairman of this session, NATO, to be responsible for the rain. And his only aim in life is going to be not to take care of agriculture or of people not dying of thirst, but to make me as a forecaster look bad. What you guys call an adversarial rainmaker, okay? I'm sorry to tell you, it won't help you. I can still generate a sequence of forecasts that is going to be calibrated, no matter what the weather will be, okay? So that's a result of Foster and Dvora, of the paper that got the award. As I said, they wrote the paper in the early 90s and kept sending it to journals, and they would just get it back after 1 week saying, this result cannot be true. Not that there is an error in the proof, but how can you do that without any assumptions on weather, okay? Now, in 5 minutes, you will get the proof of that, this result, and you will know also that this is indeed true, okay? Now, it's important to understand that we are not in a Bayesian model. We make no statistical assumptions on the frequency of rain or on the sequence of rain, no rain, nothing, okay? So we are in a worst case kind of analysis without any Bayesian or statistical assumptions. The second point to understand is that the forecaster is going to use a mixed strategy. And just not to get confused, what I mean by that is that he's going to, so for example, forecast 25% or 60%, toss a coin, and this probability half, say 25%, probability half, say 60%. That's mixed forecasting. There are many numbers here between 0 and 1. 25% and 60% of the forecast, and the probability of the various forecasts, that's a probabilistic mixture, okay? So there was the original proof of Foster and Dvora, and there is another proof, which in fact I'm going to show it to you, and that's my proof from 1995. In fact, as first time that I heard Dean Foster give the talk, I immediately came up with this proof. And let me tell you what this proof, it's very simple, okay? It uses the Minimax theorem, which I'm assuming everybody knows here, even if some of you may know it as Yao's principle, okay? That's the Minimax theorem, okay? It's exactly the same. So what is von Neumann's Minimax theorem? It says that if we are in a finite two-person zero-sum game, and we look at mixed strategies, if for every strategy, for every mixed strategy of my opponent, I can guarantee 7, I can guarantee a payoff of 7, I can obtain, I have a reply that gives me a payoff of 7, then I can guarantee 7. Namely, there is a mixed strategy of mine such that no matter what my opponent does, my payoff is going to be 7 or more, okay? That's a Minimax theorem, and I'm going to apply it very easily. Suppose that I want to get 10% calibration. So the error between forecast and what will happen is 10%, or epsilon, okay, or delta. I think in the slide here it says delta. So the error is delta, let's say 10%. So what I'm going to do, I'm going to limit myself to forecasts that are multiple of 10%. So 0%, 10%, 20%, and so on. I have 11 different forecasts every day. The rainmaker has 2 choices every day, rain or no rain. And we repeat this game for a certain number of time, let's call it capital T. Let's say 1,000 periods, okay? Or 1 year or whatever, okay? Now, the game is finite because each one of us has finite many choices and the horizon is finite. And if I know the strategy of the rainmaker, if I know the mixed strategy of the rainmaker, then of course, given the history, I know exactly what the probability that is going to choose rain tomorrow. what's my forecast going to be? Exactly that probability rounded up to 10%. Okay? If I do that, so if I know the strategy of the rainmaker, then of course I can generate calibrated forecasts because I know exactly what the probability of rain is going to be every day. And I can just forecast that with the error of 10%, with the error of my grid. Okay? Now, what the Minimax theorem says, I can guarantee it. Okay? Which is quite amazing, come to think of it. In fact, it's quite striking that one direction, namely, if I know the strategy of the rainmaker, I can get forecasts that are calibrated. Of course, I know exactly what the probability of rain is. The fact that I can then guarantee it without knowing anything is why so many editors rejected that paper. Okay? But that's just the Minimax theorem, okay, which shows you the power of the Minimax theorem. And in parentheses, I'll say, for many years, I'm giving talks on this topic, and there is a challenge to the audience, which is find me a better use of the Minimax theorem, a more striking use of the Minimax theorem. And the challenge is still up, okay? Because again, the distance between the very trivial part, if you know what the rainmaker does, you can be calibrated. Two, you can guarantee calibration is really huge, okay? And that I think is a simple but beautiful use of the Minimax theorem. Okay, so now let's go back to the previous slide. That's very good, but how do I do that? How do you get calibrated forecast? The Minimax theorem says there is a mixed strategy, but of course the game has a huge number of strategies, and that's quite difficult. So turns out that you can do it, and for that we are using some other tools, and that's the work of Andrew and myself, which is the other paper, which in fact is not about calibration, but it's related, and I'll talk about it later. And that uses a tool which is called Blackwell's approachability, which is a beautiful tool, and I'll talk about it later. Then Dean Foster took that and much simplified it and got a really simple procedure for getting calibrated forecasts. And in fact, the latest work of Dean Foster and myself, we get an even simpler procedure. In fact, it's the simplest possible procedure, okay? You don't need a computer, you just need your fingers, that's all. Really, a piece of paper, and that's it, nothing else. And you can generate calibrated forecast. It's amazingly trivial, okay? Now, the point is that all these things, all this thing is phrased in terms of forecasts. Forecast is telling something about the future. Now, I am forecasting what the rainmaker is going to choose, which I'm assuming, which I'm allowing it to be even adversarial. I mean, there is no way I can know what Renato is going to choose tomorrow, okay? No way. So all this forecasting, there is no forecasting here. What is happening here is something that we call backcasting. Namely, what is happening, I'm looking at my track record, what happened in the past, and I'm looking at my different forecasts. Some of them were right, some of them were overshooting, some of them were undershooting, and I'm choosing a probabilistic distribution in such a way that no matter what the weather will be, my track record can only improve. And that thing we call forecast hedging, and that's a beautiful principle that in fact generates all the calibration results in the literature, and there are many, in many models and many different ways, and deterministic and stochastic and so on. And that forecast hedging, which is, you see the Foster Hart paper of 2019. So you can remember forecast hedging as the right initials. That's, it's a good name that we chose. Is the right principle that unifies all these things. Okay, enough about calibration. Let's see. Well, okay, I still have some time. So let's go to regret matching. Okay, so forget everything about calibration temporarily. We'll come back to it. And now let's talk about regret matching, which is the other paper that has been belongs to this award. And what is regret matching? So regret matching says the following: we have an n-person game that is played repeatedly. Okay, and regret matching is the strategy in the repeated game. Is a way to play the repeated game that says the following: switch next period to a different action with a probability that is proportional to the regret for that action. Okay, now The word proportional, I think, is clear, but what is regret? So let me explain what regret means. Regret means by how much would my payoff have gone up, if at all, if I would have switched this way in the past, okay? So let me make this more precise. I mean, no big formulas, don't worry. Suppose that your average payoff, that my average payoff up to now is something I call capital U. And suppose that if I were to switch from my current action and play instead of it a different action K, for some K, I would have gotten instead a payoff equal V of K, okay? My regret is V of K minus U positive part, which means if V of K is bigger than U, then it's a difference. If V of K is less than U, I have no regret. My regret is 0, okay? So that's the definition of the regret for action K. And what's regret matching? I switch to action K with a probability that is proportional to that regret. The higher the regret, the more I tend to switch to that action. And with the remaining probability, I stay put and play what I was planning to do, what I played last time, sorry, okay? Now, that sounds like a very simple procedure. In fact, I could describe it in words, and I hope, despite the fact that I'm rushing, that it's still clear what I'm saying here. And here is the result. Assume that all players play regret matching. Let's look at the joint distribution of play, which means I'm counting how often every n-tuple of strategies is played. Okay, it's like looking in the matrix if it's a two-person game and counting each cell in the matrix, what is its frequency. Okay, well, that thing is essentially a correlated equilibrium of the game. Okay, that's a result of Andrea and myself. It only took us 4 years to publish it, so that's nothing. Part of it is our improving the paper, so we are not going to complain here. Now, let me give you an idea of where this result comes from, okay? So first observation is that those regrets that I'm talking about, they are very tightly connected to correlated equilibrium. Correlated equilibrium is exactly equivalent to all regrets of all players being 0, that you never want to switch to a different action. That's what correlated equilibrium means. Now, what regret matching does, it guarantees that the regrets converge to 0. So if you put those three things together, it means that if regret matching is played, then you converge to the set of correlated equilibrium. Now, how does regret matching guarantee that regrets go to 0? That's where Blackwell comes in. And Blackwell is essentially an extension of the Minimax theorem to single payoffs, from single payoffs to vector payoffs. And the vector of payoffs, so you care not only about one payoff, but you have a whole vector of payoffs, and those are exactly the regrets. And you are just making sure that all of them go to 0 simultaneously, okay? How do you do that? Well, it turns out that's quite complicated, and you have to place some eigenvector of a regret matrix. That's what comes up of the computation, which is not what regret matching was. I never said eigenvector. And indeed, part of what made regret matching such a nice procedure is translating these eigenvector things, thinking of them as the invariant distribution of a Markov chain, and then rather than looking at the limit of the Markov chain, play the Markov chain every period. I'm not sure anybody followed that, but anyway, you just play the regrets, you just use the regrets as transition probabilities, which in the long run is essentially like the Blackwell approachability thing, the eigenvector strategy, okay? Well, what I can say, the procedure is simple, the proof is quite complex. Yes, it's many pages of very, very many approximations and making sure things are okay, and also some conceptual things. Anyway, that's this result. Okay, I'm already two to go. Okay, very good. So now let me go to topic number 3, which is dynamics and equilibria. So after the regret matching paper of Andrea and myself, then we started asking ourselves, in general, we have here nice dynamics going to converging to correlated equilibria. Now, how about Nash equilibria? Nash equilibrium, everybody would like to converge to Nash equilibrium. And let me tell you, here is a fact. Okay, I call it a fact. There are no general natural dynamics leading to Nash equilibrium. Now, let's understand what I mean by that. General, I mean in all games. So of course, if you take a very special class of games, like two-person zero-sum games or potential games, then there are nice dynamics that give you Nash equilibria. But I want something that works on any game, okay? Leading to Nash equilibrium means, and we have to, sorry, means that from some point on, we are close to being a Nash equilibrium, okay? So something where you get close to Nash equilibrium, then you leave it and wander around, then at the future time you get close to it again, that doesn't count. Converging or leading to Nash equilibrium, meaning from some point on, you are close to being a Nash equilibrium. Finally, natural, what's natural, okay? So I'll just give you some hints of what we mean by natural. So it should be something like an adaptive procedure, yes? Like things that react, you improve, pay off, things of this sort. We all know what adaptive, I mean, we don't have a good solid definition, but we have an idea of what that means. We want those things to be simple and efficient, because if they require every time to solve a fixed point problem, that's not a simple procedure, and that's not a procedure that anybody does. I don't know how many of you ever solved a fixed point problem. For sure, not every day that you have to play the game. Efficient means that things should converge quickly, okay? So here I wrote a few requirements: that the computation should be easy, the time to reach equilibrium should be reasonable, not the age of the universe or beyond, and the information that players have should be, again, reasonable, okay? And what do I mean by that? So that's, again, a notion that Andreu and myself introduced, which turned out to be a very useful notion, which is a dynamic that is uncoupled. And what does it mean for a dynamic to be uncoupled? It means that each player knows only his own payoff function. So I know exactly what my objective function is. I know what my payoff is, but I have no idea what my opponent's utility function is. I can see what they do, but I really don't know what their utility is, okay? Now, that's a very natural assumption. Computer science, we call it distributed, but that appears in economics and privacy preserving, Leo Hurwitz, mechanism design, decentralized, and so on. So it's a very natural assumption, okay? Now, once we take information that's meaning uncoupledness, let me just mention another thing that for this community may be very appealing. How long does it take to reach equilibrium? So we are talking now about an uncoupled dynamic, and that turns out to be exactly equivalent to a computational procedure that is distributed. And that's an observation of Konitzer and Sandholm from 2004. And that says that the right tool to analyze how long it takes to reach equilibrium is communication complexity, because that exactly tells you how long it takes for a distributed procedure to compute something. And what you compute here, compute in quotation marks, is a Nash equilibrium, okay? Again, I'm rushing through things, I'm just throwing ideas to you. And so there is some work that I did with Ishai Mansour, and there was a tiny thing left open. In fact, was a major thing left open on epsilon equilibria that then was solved by Babichenko and by Yakov Babichenko and Aviad Rubinstein, a beautiful paper that really very, very deep and very important. Okay, so very good. Let's see. I still have, I guess, 5 minutes. Is that correct? So let me. So
ideally more like 2 or 3 minutes.
Sorry. Well, I have 3 minutes if I would have started on time, but since I started 3 minutes later, but I'll finish. I'll finish in 3. I mean, I'll finish quickly. Again, I'm going to rush through this. So what's the relation? Let's go back to calibration now, okay? We have forecasts. How to use them for dynamics? Oh, sorry, I should, okay. I see, okay, let me jump, well, I'm not sure I should jump over that. Okay, I'll say something, I'll jump over something else, okay. Let me go back to calibration for a moment and make the observation that if the forecast, go back to the Minimax term, or even without the Minimax, forget the Minimax, just the definition of calibration. If the rainmaker knows my forecast before deciding on rain or no rain, then of course I cannot be calibrated, because if my forecast is less than 50%, there will be rain, torrential rain, just to make the point. And if my forecast is above 50%, there will be sun, okay? which means that my calibration error is going to be at least 50%. Okay, so if my forecast leak, that's what we call leaky forecast, to the rainmaker, like WikiLeaks, not like roof leaking, then I cannot guarantee calibration. The same is true if I use a deterministic forecasting procedure, because the deterministic forecasting procedure says history determines what I do tomorrow, which means determines the forecast deterministically, which means the rainmaker knows what it is, and again, he's going to use the below 50, above 50 rule to make my forecast being extremely far from being calibrated, okay? However, let's modify our calibration score slightly. In fact, let's just smooth it out. And let's talk about continuous calibration, which means we combine together the days when the forecast was close to P, before computing the error. So I'm not just looking when I said 70%, I'm looking also at 69% and 71%, let's say, okay? Here is a beautiful result. I can be continuously calibrated with a deterministic procedure. So even though I'm allowing the rainmaker to know exactly what my forecast is, I can guarantee continuous calibration, okay? And some version of that was due to Foster and Cacade, and then there is work of Dean Foster and myself. And okay, why is it important? So I'm finishing now. How to use calibration? Well, people can forecast what's going to happen next period, and then respond to those forecasts. If the forecasts are good, which means calibrated, and the responses are good, which means they use best responses, then in the long run, hopefully we get some nice equilibrium, okay? So one such result, I'm doing it very quickly, is use calibrated forecasts, best reply to it, you get correlated equilibria. That's another paper of Foster and Vora from the 90s. On the other hand, use continuously calibrated deterministic forecasts, then 1 minus epsilon of the time, you are close to being a Nash equilibrium. You are playing an epsilon Nash equilibrium, okay? And that's again, work of Foster and Cacade and Foster and Hart that I mentioned. And so I'm finishing now with a nice table that says the following. Look, there are really two universes out there, two parallel universes. One we are calling the Minimax universe, the other we are calling the fixed point universe. In the Minimax universe, we have stochastic forecast hedging, and in the fixed point universe, we have deterministic forecast hedging. We have, here is for the computer science people, P procedures, polynomial, I mean, and P-path procedures, which everybody in this crowd knows, in the fixed point world. We have classic calibration obtained by Minimax. We have continuous calibration obtained by fixed point methods. Correlated equilibria in dynamic setups versus Nash equilibria in the fixed point setup. Here we obtain this as a time average. In the fixed point universe, we obtain this period by period. In the Minimax universe, from some time on, in the fixed point universe, most of the time. So there is really a nice dichotomy here between the Minimax and the fixed point universe. You have parallel things all along, and it's a nice way to organize everything that we know. And that's the end. And here is my attempt to tell you about dynamics and equilibrium. Okay, it was very old technology. I'm sure you and I would have done it something better, but that's very old technology. And thank you all for listening. As I said, if you have questions or things, you can look on my webpage, and there are links there. And of course, any questions anytime.
Thank you, Sergiu, for the great talk. I think it passed the test of time in both ways.
Yes. So, I even did it in 29 minutes.